It's finally IA season, yay! Which means here's another review video with your boy Mapoy. Okay, so this one is all about atomic structure. We didn't get too far, we kind of finished this unit pretty early on, but I hope you guys have been working on this practice exam. I gave you guys a week in advance to the IA. And so right here there's about 20 or close to 30 questions on this practice exam. They're Regent style. These are the questions we kind of gave last year, and so we expect you guys to be able to live up to that same standard. And also we have here is our handy dandy reference table right here, which is going to be helpful for some questions. And so let's begin with number 1. Well, actually, before we even begin, I want to point out, if you guys are here just for the answers, you could probably skip to the end and you'll see the answer key. But if you want the step-by-step how each question is done, then follow along with this video. And so let's actually begin with number 1. Sorry about that. Alright, so number 1, which atom in the ground state has the same electron configuration as a calcium ion Ca2+ in the ground state? That's a lot to do. Alright, so first let's pull out our reference table. Find calcium. Oops. I need to expand this sucker. Okay, calcium. Calcium is right here, number 20. So let's decrease the size of this guy. And find our electron configuration. So the electron configuration for Ca in the ground state is 2, 8, 8, 2. Ca2 plus, now because it has a charge of 2 plus, this means it lost 2 electrons. So it has 2 less electrons than the normal Ca ion. So that means our electron configuration for Ca2 plus will be 2, 8, 8. And if we look at the element, we're looking for the element that has that ground state electron configuration. So we look for the element that is 288. Where's my highlighter? And 288 will be this one right here, argon number 18. So our answer here is choice 2 for number 1. Alright, let's put this away. Which electron configuration represents an atom of chlorine in an excited state? Alright, so chlorine in the excited state should see a different configuration than its normal ground state. So let's find chlorine on the reference table. Chlorine is right here, number 17, so it's 287. 287. In the excited state, what you want to do is take an electron from the lower level, let's say this one, and bring it up to the higher level. So instead becomes 2, 7, 8. So you take one from a lower level and bring it up to a higher level. That's what excitation is. And so if we match it up, 2, 7, 8 is one of the choices. That is choice 4. Okay. Number 3. Compared to the energy and charge of the electrons in the first shell of a Be atom, the electrons in the second shell of this atom have. So let's think about shells. Shells meaning energy levels. The higher number, the more energy it has. So second level, second shell, should have more energy than the first shell. So we could cross off 3 and 4. We're focusing on more energy. But electrons, their charge is always negative, so it stays the same. Alright, so that's number 3 done, out of the way. So we got 2, 4, 2 as our first 3 choices. Alright, let's move this out of the way. Which statement describes a concept included in the wave mechanical model? So wave mechanical model talks a lot about, let me shrink this guy down, put him in the corner, bye-bye. Okay, wave mechanical model, we focus on this idea of orbitals. And these guys are locations for electrons. These are where electrons are located most probably. So electrons are located in orbitals outside the nucleus. That's the most accurate answer. So remember that orbitals are places where electrons are held. They are the most likely location for electrons. All right, number 5. Which notations represent hydrogen isotopes? So this requires us to know what the word isotope means. So isotope meaning same element, different mass numbers. As a result, different number of neutrons. Okay? So that means we should all see hydrogen and the same atomic number because it's the same element. So if we look at our choices, we can cross off choice 1, 2, and 4. That leaves us with choice 3. So if you look at the bottom number, right here, 1 and 1, that's the atomic number. That's also the same number of protons, so it's the same for hydrogen. These top numbers here show the different mass numbers. All right. Now, number 6, which particle has 2 neutrons? So that means, how do we find that out? All right, number 6. So that means you want to be able to compare the top number and the bottom number. So in these examples, you have a top number and a bottom number. Bottom number tells you atomic number, and it's the same as the number of protons. Top number is mass number, tells you both protons and neutrons. So if we look at choice 1, 2H1, so 1 proton, so that means the rest of this number in 2 leaves you with 1 neutron. So it can't be choice 1. Now choice 2 is just 1 neutron, so it can't be choice 2 either. Now if we look at choice 3, it's going to be our correct answer. Why? So we have 2 protons here for helium. So 2 protons, that means the rest of this here is 2 neutrons. And if we look at choice 4, 1, 1, it can't be. There's no neutrons here. So it has to be choice 3. Alright, and then number 7, an atom has 13 protons. So this also tells you atomic number. So 13 protons, you gotta look it up on the reference table. Let's look. Alright, looking at number 13, 13 protons, it's aluminum. Alright. Alright, number 8, the atomic mass of magnesium is the weighted average of the atomic masses of. So this is a basic definition kind of question, you just need to know. So average atomic mass has to deal with all of the naturally occurring isotopes. None of this artificial BS. None of this man-made stuff. It's all naturally occurring, regardless if they're the most abundant or least abundant. It's all natural. Alright, next. Number 9. Which quantity can vary among atoms of the same element? What can vary? So if we're talking about the same element, it can't be number of protons. So the number of protons tell you identity. They tell you the element. Number of neutrons help you with mass number. So they can be the same element but different masses. And the number of electrons tell you what the charge. But if you change the number of electrons, you make an ion, not an atom. So it's not a neutral atom, but a charged ion. So if we look at each of our choices, number of protons and atomic number are the same thing. So we could cross off 1 and 3. Can't be. So we're down to mass number of electrons. So we focus on atom. So it's not number of electrons because these deal with ions, whereas mass number is the only eligible choice. Alright. Number 10, the mass of a proton is approximately equal to 1 atomic mass unit. So that's something you just need to know. So mass of protons, same as mass of neutron. Electrons, practically 0. Alright, number 11, all phosphorus atoms have the same atomic number. That pretty much identifies the element. Number 12, what is the charge of the nucleus of an oxygen atom? So let's think about what goes inside the nucleus. So it's both protons and neutrons. Okay? And so protons, they have a charge of +1, neutrons have 0. So oxygen here has how many protons? It's the number 8. It's the 8th element, so it has 8 protons. Since neutrons have no charge, it's just 0, so all of this here is a charge of +8 in the nucleus. Where are those electrons? They're outside, so they don't count here. Now number 13, which conclusion was drawn from the results of the gold foil experiment? So this you just need to remember. An atom is mostly empty space. That's why we saw a lot of the helium particles, the alpha particles go through the foil. And it's the same thing with the paper ball experiment. Most of those paper balls went past me. Number 14, which statement describes the distribution of charge in an atom? So let's think about the basic model of an atom. So you have the nucleus, which is the dense center, and then you have the rest of this electron cloud here with all the electrons and these orbitals. So these electrons are in there, they're all negatives, somewhere here, here, and there. And then inside the nucleus are all positives and zeros, positives and zeros, positives and zeros. So that means the center, the nucleus, is positive. And then it's surrounded by what we call the negative particles, the electrons. So it's a positive center with negative particles surrounding it. So that means we could cross off 3 and 4. We're left with 1 and 2 for positively charged nucleus surrounded by negatively charged electrons. Choice 2. Number 15, compared to the charge of the proton, the charge of an electron has, alright, so protons and electrons. This one's +1, this one is -1. It's the same number, same magnitude. So this is the same magnitude, opposite sign. Number 16, what is the overall charge of an atom? Overall charge of an ion that has 12 protons, 10 electrons, and 14 neutrons. So 12 protons. Protons are +1. And then we have 10 electrons. And then 14 neutrons. Neutrons don't count. So this here is 12 minus 10 equals a +2 charge. Number 17, which particles have approximately the same mass? Automatically choice 1, proton and neutron. Number 18, an atom of lithium-7. So lithium-7 meaning 7 equals mass number. So lithium is our third element of the reference table, of the periodic table. So that means it has 3 protons as well as 4 neutrons to add up to 7. So 4 neutrons, 3 protons add up to 7. So it can't be the same number of protons and neutrons. Can't be that. So it can't be also electrons and neutrons. Can't be positrons because we never talked about positrons, so that leaves us with electrons and protons. So that one's a weird example, even though we've once said it was protons and neutrons. But here, if we actually do the math, you'll see that protons and neutrons are different. So that leaves us with protons and electrons. All right, number 19 has 2 electrons in its first shell and 6 electrons in the second shell. So that means it has electron configuration of 2, 6. If you look at electron configurations, the total number here should equal the same as the atomic number. So 2 in the first, 6 in the second, that's a total of 8. 8 total of electrons, which means it's the same number of protons there. Now number 20. Which Lewis electron dot diagram represents a nitrogen atom in the ground state? Okay. So in the ground state, well, let's not even focus on the ground state. Let's focus on Lewis electron dot diagram. So these guys use valence electrons. So valence electrons are the last number in the electron configuration. So let me pause this for a moment. So what I want you guys to focus on is looking at nitrogen. Electron configuration is down here, 2-5. The valence electrons is basically the number, the last number of the configuration. So for nitrogen, it's 5. So we have 5 valence electrons, and we represent them as dots in this Lewis electron dot diagram. So what does it look like? You need to draw the symbol N with 5 dots. 1, 2, always 2 on the top, and the rest you fill out around the area. So 5 dots. So that gives us choice 2. Alright, number 21, we here have bright line spectrum. So here when you have bands of different elements and they give you a mysterious spectrum, mysterious element, you need to figure out which ones are in the mixtures based on the matching line. So 21 asks which elements are present in the mixture. So if this one right here is our mixture, we need to see which of these 4 match up. So if we look at these, we have a line here in between 700 and 650. This matches up this line over here. We also have another line close to 600. That's this line here and this line over here. Then we have 2 lines after 600. And then so it's these 2 lines here. And then we have a line on 500. It's this line and this line. And then we have this one close to 450. So we got this line. And not quite the other line. And that's it. So we need to find the ones that match it all up. If you see element X here, not all of them are filled out. And it's not the same with element Z as well. So it can't be these 2. So it's not these 2. But if you look at element A and D, all of their bands are highlighted and matched with the mixture. So if they all match for a single element, then they're present in the mixture. So these 2 are in there. So it's A and D, choice 1. Alright, this prompt is for 22 to 24. State how bright line spectra viewed through a spectroscope can be used to identify the metal ions in the salts used in the flame test. So this spectroscope is a device that shows the pattern. So it's basically, it shows these patterns up above right here. So the device shows pattern, and each element has characteristic pattern. So like sodium would have its own pattern versus something like strontium. They each have their own pattern, so if you're able to use the device to see the patterns, you can identify it based on the pattern. Oops, let me finish that. Okay. Now, number 23, explain in terms of electrons how a strontium salt emits colored light. So electrons get excited. And so they release that excitation energy, release energy in form of light. And then number 24, explain why the electron configuration 2711 represents a sodium atom in an excited state. Because if you look at sodium on the reference table, it should look like 28-1, 281, that's ground state. And when you compare it, 2711 is an excited state. You take one from a lower level, bring it up to a higher level, and that's it. Alright, number 25. Here we get isotopes of potassium, 1, 2, 3, 4, 5. 5 different isotopes. So if you look at each of these isotopes, they're all potassium, K, 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 K. But each of the numbers are different. They show different mass numbers, so the number of protons are the same, but neutrons are different. Okay, and so we need to show a numerical setup for calculating the atomic mass of potassium. So we're going to take all of these into account, natural occurring. And so they only gave us 3 of the natural occurring ones. So how do we show this? We're going to take each of these natural abundances and multiply by the atomic masses. However, these percentages have to be into decimal form. What does that look like? Let's start with the first one. So we take 0.9326, take the decimal point and move it to the left twice for decimal, multiply by 38.96 plus 0.00001, okay, times 39.96, and then another plus of 0.0673 times 40.96. So you take each of these percentages, convert them to decimals, and then multiply across, and then add them all up. And that's it for a numerical setup. Now, number 26, here we're talking about the Bohr model. State the atomic number and the mass of this element. So it has 4 protons. 4 protons leads us to an atomic number of 4. So this is beryllium. The mass number, because it has 5 neutrons, 4 plus 5 gets us a mass number of 9. So we just need to state these two numbers, so 4 and 9. So that's beryllium. Alright, as promised, here's the answer key for the multiple choice sections. I decided not to put it up for the free response section. You should go turn back to the last few slides just to double check your answers. But anyway, here's the answer key as promised. Multiple choice answers here, just like your IA. And if you have any other questions, feel free to reach out to me. And yes, best of luck, guys.